Okay, so we defined the buoyancy frequency as G over theta E, where theta is the dry potential temperature, uh, and E is of course still the environment. D theta E dz is the dry adiabatic lapse rate in potential temperature. We see that here, we saw before. So that's the ambient temperature profile, which we said is T is not conserved because of compressibility effects, whereas potential temperature takes into account the compressibility, and it is conserved in dry processes. We haven't defined moist potential temperature yet, but we will do that. So for a typical tropospheric profile, you can estimate n squared with G theta E and d theta dz as a change over certain pressure height divided by the distance delta z, right? So that's 1.3 times 10 to the minus 4 per second squared. So that's a frequency. So this is seen here. What can we do with it? You can estimate the period of the gravity waves. 2 pi over n is about 9 minutes, and you can see a schematic of ways to generate gravity waves. Here is a flow that's coming along, hitting a mountain. It has to rise, expand, cool. The moisture in it is going to condense. You may generate distinct clouds types over the mountain known as the lenticular cloud, which we will see in a minute of a picture. Downstream in aloft, cloud bands may mark parts of the wave train depending on the background winds and how long the wave can be sustained based on other conditions. But essentially, when the wave has these crests and troughs, you're obviously going to expand and then compress and create potentially the clouds. The specific type of cloud, lenticular cloud, is really magnificent to look at. If you haven't looked at, if you haven't seen one before, keep an eye out next time you see, and you can explain to grandma why this is a lenticular cloud and how it is produced by gravity waves. You can also estimate the wind speeds required given the buoyancy frequency, the wavelength, and the potential for stationary waves. So we had n 2 pi over n of 9 minutes, and you get a wavelength for about 5 to 10 kilometers if the wind is about 10 to 20 meter per second. So simple calculations, but nonetheless you can kind of go try to do that when you're next time out on a hike. There are places, this is the continental divide of North America, which the Rocky Mountains provide a nice long north-south range of mountains that are in the way of the westerlies that are forced to rise. And in fact, there is some studies that show that the waves generated by the Rockies go all the way to Europe, and maybe in fact responsible for picking up the heat from the Gulf Stream region and taking it over to Europe, and that being responsible for the huge difference in temperatures at the same latitude between the eastern coast of US and Europe, like UK for example, compared to some place in the northeast which gets much colder, whereas UK is drizzly and warmer, right? Richard Seeger wrote a nice story on that you can look up from Columbia University Lamont Doherty Earth Observatory. Another example of gravity waves is here from Jan Mayen. It may be pronounced Jan Mayen Island in Iceland. So there's a volcanic island here which is about 50 kilometers long, 375 miles north-northeast of Iceland, and also has a unique flow, westerly still, that flow over the volcanic island that's stretched along here. And you can see that even a ship that's in here can produce crests and waves in the ocean, whereas these are the gravity waves that are produced in the atmosphere. Okay, so the atmospheric gravity waves and the ship's wake have somewhat similar features, because those are also internal gravity waves produced by perturbing the stratification of the ocean waters. Okay, similar phenomenon. We'll do the ocean later on, but we have to go forward now and define temperature inversions, another thing that comes out of this various processes that we have been discussing so far. We'll see that before we go on to moist convection and moist potential temperature and so on.